Okay, in this class, I want to talk about network compression. In this class, we have seen a lot of huge models. For example, BERT or GPT. In this lecture, the thing we want to share with you is, can we shrink these huge models? Can we simplify these models? Let it have a relatively small number of parameters, but has almost the same performance as the original. This is what network compression does. Why do we care about network compression? Because many times, we need to use these models in resource-constrained environment. In environments with limited resources. What kind of environment has limited resources? Sometimes you will need to run these machine learning models. For example, on a smartwatch. Or on drones. On these edge devices. On these IoT devices. Only a small amount of memory is provided. There is only a relatively small computing power. So if our model is too huge, your watch may not run successfully. So we will need smaller models. When it comes to this, someone may ask, why we need to run models on these edge devices? Why don't we send the data to the cloud and do the calculations directly on the cloud? Then we send the result back to the edge device. For example, your watch. Why do you have to do calculations on the watch? The common reason is the latency problem. Suppose you need to transfer data to the cloud today. After the cloud computing is completed, and we send it back, there will be a time difference. Suppose your application, on your edge device, is a sensor for self-driving cars. Then maybe the sensor of a self-driving car need to make a very immediate response. You need to transfer the data to the cloud and then back. The latency is too long. Perhaps it is too long to be acceptable. Then someone will ask again, will the latency be ignored at all in the 5G era in the future? Then someone will give you another reason for running models on the edge device. This reason is privacy. If we need to transfer data to the cloud, the system owner in the cloud can see our information. Maybe what I don't want cloud system owners to know what I'm doing. So to protect privacy, the calculations are done directly on the smartwatch. And decisions are made directly on the smartwatch, which is a way to protect privacy. Okay, I just tell everyone various reasons for network compression. In this slideshow, I will introduce 5 technologies for network compression to you. These 5 technologies are software-oriented. We work on the software to compress the network. We don't consider the hardware acceleration part. Of course, another branch of the study does. Think of ways to speed up the calculation of the model on the hardware. Making edge device run deep learning more efficient. But this is another direction of research. We won't discuss anything related to hardware here. We only discuss things related to software. Okay, the first one I want to share with you is the method called network pruning. After we finish network pruning, we will call it a day. Network pruning, literally, is that we need to cut of some parameters in network. Pruning means cutting of. We select some parameters in network and cut them off. Why can we cut off some parameters in network? Because there is a saying goes, there's a black sheep in every flock. In such a big network, there are many parameters. Not every parameter is useful. When there are so many parameters, maybe many parameters are useless. They don't have any functions. They do nothing. The parameters that are useless are just take up space. They waste our computing resources. Why not just cut them off? So the basic concept of network pruning is to find out those useless parameters in a big network and cut them off. When I was a kid, maybe not that young, in my high school, I saw this picture in the biology textbook. It has some relation with network pruning. This picture tells us that when a human was born, there is nothing in our brain. These pictures are the neurons of the brain. There is nothing in our brain. There are few connections between neurons and neurons. A lot of connections will appear at the age of 6. But with aging, some connections slowly disappeared. There are lots of similarities between this thing and network pruning. Actually, network pruning is not a new concept. Back in the 90s, Jan LeCun had a paper which talked about network pruning. The title of the paper is Optimal Brain Damage. He said that network pruning, which cut off some weight, could be seen as a kind of brain damage. A damage of brain. Here, optimal means that we want to find the best pruning method. Even some weights are cut off. The damage to this brain is small. Okay, how does network pruning work? Its framework looks like this. First of all, we train a largest network. We train a big network. And then, in this big network, you measure the importance of every parameter, or every neuron, to check that whether there are any parameters which don't do nothing, or are there any neurons doing nothing? How to evaluate whether a parameter is doing something. How to evaluate the importance of a parameter. Perhaps the easiest way is to check its absolute value. If the absolute value of this parameter is large, it may have a great impact on the entire network. If the absolute value is closer to 0, it may have less impact on the entire network. You can borrow ideas from lifelong learning. Do you remember that in lifelong learning, we also want to find which parameters are more important? There are a lot of methods to find the importance of parameters and then determine the BI of the parameters. Maybe we can calculate the BI of each parameter, and then we can know which parameter is more important. We can prune less important parameters. We can also evaluate the importance of a neuron. We can also use neurons as pruning units. How do we evaluate the importance of a neuron? You can count the number of times the neuron output is not 0. There are many ways to judge whether a parameter or a neuron is important. We won't go into details here. Prune unimportant neurons, or unimportant parameters. Remove them from the model, and you will get a relatively small network. After you finish this pruning, your accuracy will usually drop a little. Because some parameters have been pruned, this network is damaged. The accuracy rate drops a little. We will find a way to make the correct rate rise again. How to make the accuracy rate rise again? We can fine-tune the relatively small network on those remaining parameters. Use our training data to retrain this relatively small network. After retraining, you can re-evaluate the model accuracy. You can prune more parameters after retraining, and then re-fine-tuning. This process can be repeated many times. Why don't we cut out a large number of parameters at once? In experiments, pruning a large number of parameters at once does too much damage to your network. It might be too big to recover by fine-tuning. Prune a few parameters at a time. For example, prune 10% of the parameters, and then retrain. Then prune 10% of the parameters again, and retrain again. Repeat this process. Can prune more parameters. After your network is small enough, the whole process stops. You get a relatively small network. The accuracy of this smaller network may not be much different from that of the larger network. We just talked about that. The pruning unit can be either parameters or neurons. What is the difference between using the two units? There will be a significant difference in the implementation of using the two as a unit. What will happen if we take the parameter as the unit? Suppose we want to decide whether a certain parameter should be removed. Can a certain parameter, which is not important for the whole task, be removed? And after we remove this unimportant parameter, we might get a network which is irregular. What does irregular mean? For example, let's look at the red neuron. It connects to 3 green neurons. However, the second red neuron only connects to 2 green neurons. Moreover, this red neuron only gets inputs from 2 blue neurons. But this red neuron, on the other hand, has 4. Hence, if you prune the parameter as a unit, you might get a irregular network. After pruning, what kind of the problems can the irregular shape cause? The biggest problem is that it is hard to implement. Think about it. There is no way you can implement the irregularly shaped network using PyTorch. In PyTorch, when you are defining a network, what you need to do is to specify the number of neurons on each layer. You specify how many inputs are for each layer, how many neurons in the input layer, and how many neurons in the output layer. What is the dimension of the input? And what is the dimension of the output? So it's hard to implement such a network with irregular shape. It's hard to implement by yourself. Even if you eventually implement such a network, you might find it hard to use the GPU acceleration. The acceleration of GPU is to consider the calculation of network as matrix multiplications. So when the network is irregular, it becomes difficult to speed up with matrix multiplication. Actually, in practice, You can simply assign 0 to the weights pruned. When doing weight pruning, that is to say, it still exists, but the value is 0. It turns out that your implementation is easier. It's easier for you to use GPU acceleration. However, another problem emerges. The problem is, you didn't really make your network smaller at all. You assign a 0 to the parameter in your network. Then the parameter is still saved. The parameter is still located in your memory. You didn't really make the network smaller. You just make it smaller in your imagination. You are getting hyped by yourself. You think this network has become smaller. But actually it hasn't. So this is the problem you will encounter when doing pruning in the units of parameters. The experiment is only to show you what kind of problems you will encounter when doing pruning by the units of parameters. We first look at the purple line here. The purple line here is sparsity, as it says. What does this sparsity mean? This sparsity means the percentage of parameters which are dropped by pruning. Then, you find out that the value of this purple line here is very close to 1. What does it mean? It means that there are nearly 95% of the parameters which are dropped by pruning. This network pruning method is actually a very efficient method. Usually, you can prune off more than 95% of the parameters with only 1 to 2% accuracy dropping. So, parameters are pruned here. They are pruned severely. 95% of the parameters are pruned. Originally, since 95% of the parameters are pruned, and only 5% of the parameters remain, this network should become very small, and its operation should be sped up. But, in fact, it is not much sped up at all. We can even say that it is not sped up at all. If you look at these bar graphs show, on 3 different computing resources, the speed up level, which is how fast your speed up level is. The speed up level must be greater than 1 to be recognized as speed up. If the speed up level is less than 1, it actually slows down. You found out that, in most cases, there is no speed up at all. In most cases, it actually slows down. Thus, you prune some weights off. As a result, the shape of your network becomes irregular. And then, when you use the GPU to accelerate, you can't really speed it up. So, weight pruning might not be an effective method. Then neuron pruning, which is pruning in units of neurons, might be a much effective method. If we use neurons as a unit to prune, after forsaking some neurons, the architecture of your network is still regular. In brief, it's easier to be implemented for you while using PyTorch. When you are going to implement it, you only need to change the input and output dimension of each layer. So, it's easier for you to implement it. It's also easier to accelerate it with GPU. During the implementation of network pruning, there are issues that you may encounter. Okay, we would take a look at the questions if anyone asked. Let's see. Pruning. Some students asked about this pruning. Should it be the Chinese character of scissoring or reducing? In my opinion, it is a scissoring. But, if I make a mistake, please correct me. A classmate asked that, if I do pruning in CNN, which will prune some parameters off in the mask, is the computation unchanged? I'm sorry. I don't understand this problem very well. What is prune some parameters off in the mask? I can't get it here. Maybe, you can reformulate your question, and I'll look at it later. Another classmate asked that, the efficiency of this pruning is a matter of the function library. Yes, it's a matter of the function library. If you can think of a way to build an effective function library for a regular network, you can use weight pruning. But, the problem is, everyone doesn't want to build their own function library. All you do is calling PyTorch. So, if you use weight pruning, there is no way to speed up. If you think about it in another way, when dealing with a task, will gradually expanding the network perform better than using the big network directly? A classmate asked, if we train a small network first, then gradually make it bigger, would it be better? We just said, in network pruning, large network gets smaller gradually. If we train the small network first, then make it bigger, will it be better? The answer is no. We will answer your question on the next slide. A student said, scalable network is inherently difficult to train. Yes, a scalable network is inherently difficult to train. Okay. Now, we have to ask a question. We said we train a big network first, then make it smaller. Moreover, the small network and the large network have similar accuracy. Then why don't we train a small network directly? Train a small one directly is more efficient, right? Why train a large network then make it smaller? It's unnecessary. Why not directly train the small network? Well, the general answer is bigger networks are easier to train. You will find that if you train a small network directly, you often can't get the same accuracy as the big network. You can train a big network first and make it smaller. The accuracy won't drop too much. But going directly to the small network, you can't get the same accuracy as the one you get after pruning the big network. As for why the big network is easier to train, you can refer to this link below. I have attempted to explain this in past courses. Okay, but why is a big network easier to train? There is a hypothesis called the lottery ticket hypothesis. Since it is called a hypothesis, it is not fully proven. It's not a theory. If it has been proven, then it is a theory. But it's just a hypothesis now. How does this lottery ticket hypothesis explain why a large network is easier to train, and why training a small network directly can't get the same result as training a big network? Then prune it to become smaller? The lottery ticket hypothesis says that we know that luck is very important in training networks. Having done so much homework now, I believe you must have experienced a lot of sweat and tears. And you know that training network is all about luck. The results of the training may not be the same every time. If you get a good set of initial parameters, and you will get good results. If you draw a set of bad initial parameters, you will get bad results. Looking at this, lottery game is also a matter of luck. But how to get a higher winning rate? In the lottery game? You can buy all the tickets. Buy more lottery tickets. And you can increase your winning rate. So it's the same for a large network. A big network can be regarded as a combination of many small sub-networks. We can think of it as a big network that contains a lot of small networks. When we train the big network, we are actually training many small networks at the same time. Not every small network would be able to be successfully trained. A successful training does not mean that it could find a good solution. Through gradient descent, we may not be able to get a good result. That lowers the loss. But, among those sub-networks, we only need one of them to work to count as a success. If one of the sub-networks succeeded, it would also be a win for the big network. If the big network contains more small networks, it would be like buying more tickets for the lottery. The more tickets you have, the higher the chance of winning. So, the larger the network, the more likely it could be successfully trained. How is the big lottery hypothesis confirmed experimentally? The way it is confirmed is highly related to network pruning. Let's take a look at how it's confirmed experimentally. Okay, suppose we have a big network. In the beginning, the parameters of this big network are randomly initialized. After initializing the parameters randomly, we get a set of trained parameters, which we will represent them with purple color. Next, we use the technology of network pruning to discard some purple parameters and get a relatively small network. Now, if we directly initialize the parameters of the small network randomly again, it would be the same as training a small network of the same size again. It would be like copying the small network and training a new model with the same size, but different parameters. You'll find that training this small network directly would be unsuccessful. It is doable to train a big one and then make it smaller, but we can't directly train small networks. However, if we reinitialize the parameters of the small network with the same parameters of the red parameters, the training would be successful. Do you guys get the difference between the two? Although these two sets of parameters were all randomly initialized, the set of green parameters has nothing to do with the set of red parameters. However, these randomly initialized red parameters are picked from the corresponding red parameters back here. For instance, these 4 parameters here were copied directly from the corresponding parameters back here. Same for these ones on the bottom. They were also directly copied from the corresponding parameters back here. This way, the training could be done. We can use the lottery ticket hypothesis to explain this. There are a lot of subnetworks in this network. This particular subset of initial parameters is the lucky subset that gives good results after training. So if you already have a trained large network, the parameters that survive after pruning are the lucky parameters that can be trained. This subset of the parameters is the best subset that can be trained. But if you reinitialize this subset randomly, there is a possibility that you draw a set of bad parameters. This concludes the lottery ticket hypothesis. The hypothesis is very well known. It received the Best Paper Award at ICLR 2019. So it is a very well-known hypothesis. There are also many follow-up studies. For example, there is an interesting paper called Deconstructing Lottery Tickets. Let's directly talk about some interesting conclusions. First, the researchers tried out various pruning strategies and discovered that two particular pruning strategies are the most effective. We won't talk about the details. They did a complete experiment on different pruning strategies and concluded that if the difference of the absolute value before and after training is larger, then the pruning is more effective. The other result is related to initialization. What makes an initialization good? The conclusion is, as long as we don't change the sign of the parameters, the parameters are trainable. More specifically, the parameters refer to those in the subnetwork. What does that mean? For example, let's take a look at the randomly initialized parameters in the subnetwork. Suppose they are 0.9, 3.1, -9.1, and 8.5. According to the paper, you can completely ignore these numbers. You can replace all positive numbers with positive alpha, and replace all negative numbers with negative alpha. The new parameters are still trainable. The result get from this set of parameters is not that different from this one. The conclusion suggests that the sign of the parameters is the key to training. Compared to the signs, the absolute values are not that different. Interestingly, the researchers played a pun in the title. You would think that the paper is related to the significance of initial weights, but note that there is a. So what they are actually talking about is the significance of the sign. They played a good pun in the title, but no one seems to notice it. There is a magical discovery. It found that, since we were thinking about, there are some subnetworks with good initialization parameters in the big network. The subnetworks will be trained very smoothly. In a big network, will there be a subnetwork that doesn't even need training? Just take it out and it will be a good network? We don't need to train the network at all. We just prune the big network and get a classifier that can be used for classification. Could it be like this? It's like Michelangelo said that. How he sculpted the statue of David. He didn't sculpt a statue of David. He released David from the stone. The statue of David turned out to be inside the stone. It was in the stone. He just carved out the extra space. Removed the extra space. In the big network, whose parameters are all random, will there be a set of parameters that can already be used to classify? Remove the redundant part and get good classification results directly. The answer is like this. You can read that paper by yourself. It can get the correct rate. That is close to supervised learning. When I read this paper, this conclusion doesn't make me feel very magical anymore. Because a few months before the paper of Deconstructing Lottery Tickets is published, there is a paper called Weights Agnostic Neural Networks. It made a magical network. In this network, all the values are random, or all are set to 1.5. As a result, this network can also get a certain degree of results. It looks like even the parameters in your network are all random, or given constants. It is also possible to get good performance. This conclusion is not particularly surprising, because there was the same paper a few months ago. I put these two papers here. Archive has a similar argument. Here are the archive links of these two papers. The link here is the last version they uploaded to archive. So if you look at the month of the last upload, you will think, Weight Agnostic Networks is published later. Deconstructing lottery tickets is published first. But if you look at the first uploaded version, weight agnostic networks is earlier than deconstructing lottery tickets. So, I read this first and then read the deconstructing lottery tickets. Is the lottery hypothesis must be right? Not necessarily. There is a paper that disagreed with the lottery hypothesis. This paper is called Rethinking the Value of Network Pruning. And the magic is that this paper is published at the same time as the lottery hypothesis. They appeared at ICLR 2019 at the same time. So there are two papers in ICLR 2019. And they got different conclusions. What does that paper say? This paper says that it tried two datasets. And there are several different models. Okay, then. It says that this is the correct rate of the network without pruning. Then, it tried to do network pruning. And do fine-tune again. The small network can get the same correct rate as the big network. It says that the imagination of ordinary people is like this. If we directly train the small network, the correct rate is not as good as that of a large network. After pruning, it tries the first experiment, called Scratch-E. Scratch-E means its parameters are initialized randomly. Notice that its random initialization is not the same as the random initialization in the big lottery hypothesis. Its random initialization is really random initialization. The random initialization in the big lottery hypothesis is to borrow the random parameters from the original set of the random parameters. I know it's difficult to understand. I hope you know what I'm talking about. Good. The Scratch-E here means we really initialize the parameters randomly. The size of a small network and the size of the pruning network are the same. It found it was a little bit worse. It seems to be the same as most people's imagination. But then, what happens if we update for more epochs? The number of epochs is set by the previous person. The number of epochs trainings for a small network are the same as the big network. But what if the number of epochs of the small network is set a bit more? If we set it a bit more, it's better than the results after pruning. So before we think that the small network cannot be trained, we need to train the big ones first and do the pruning. Is this an illusion? It's just an illusion. It's an urban legend. You directly train a small network. With more epochs, it can be trained. That's it. Actually, this article, at the time of ICLR review, the reviewer asked that it's the opposite of the big lottery hypothesis. Did you have any comments? Actually, this article also responds to the big lottery hypothesis. It thinks the observation observed by the big lottery hypothesis may only be observed under certain specific circumstances. According to the experiment in this article, it's observed when the learning rate is relatively low or unstructured. Unstructured means, when doing pruning, it uses weight as the unit of pruning, which can observe the phenomenon of the big lottery hypothesis. It finds that when the learning rate is increased, it cannot observe the phenomenon of the big lottery hypothesis. So, in the end, whether the big lottery hypothesis is true or false needs more research to confirm.